Good day. So today I want to talk about kind of what eventually led up to magnets and generators. We're going to build up the information a little bit. We will kind of finish before we get to describing how motors and generators work, but at least we're going to see why the certain parts that we see here are relevant. So the main concept that we're going to get to is the significance of this loop right here within the generator or the motor itself. And then next lecture we'll talk about how the loops itself eventually become into motion. So before we get there, we have to understand how we eventually got to this technology. It had to do with Michael Faraday. So Faraday came up with a really cool idea or discovery, was that as he passed electricity through a wire in this case, so here's electrons moving in this direction, up the wire, down the wire, through the mercury, back into the battery, he found that this wire right here, actually the entire wire, will create a magnetic field. And he was able to prove that because as this wire was dipped in mercury, which also conducts electricity, this thing will start rotating in a circle. And because of that, he understood that there must be a magnetic field here. So as current is going through, it creates a magnetic field. That magnetic field is going to be making this physical wire kind of rotate or dance around the permanent magnet that's inside. So he was the first that converted electrical energy into mechanical, and that's very important. So before him, even though lights were very, very important, it was one aspect of electricity. So we want electricity to do more, and motion is a huge deal, or mechanical. It powers the cars, powers motors, and pretty much the main source was combustion. So this was just another form of way to make mechanical work from electricity. So it's just expanding the properties. At the same time, he was able to prove it backwards. He was able to show that mechanical energy could be changed into electrical energy, which was a huge deal. So this was the next thing that he created. He had a copper disc, and then he had a magnet right here. And, he had a copper disc and a magnet right here. So what he did was the exact opposite. Before he had the electricity go through the wire, create a magnetic field here. Instead of electricity, he's going to create a mechanical motion. He's going to crank this thing going around. And so the copper is going to spin through this magnetic field. And what was cool is as it's spinning, it kind of acted like a current. But as this copper is going through the magnets, what it does is started conducting electricity. So he created the first motor and first generator. And eventually we'll come back to it like the intro picture and explain kind of how that even works. But first, before we get there, we need to understand magnetism. So magnetism has been around. People understood properties of magnets. I asked you to watch videos of it on Thursday or Friday. Main thing is kind of summarized in this picture. You have magnetic fields going from one end to another. You have mini magnets right here in the compasses that kind of orient itself in certain invisible lines. So here's another picture. The magnet is underneath a piece of paper. Iron filings made of iron, and you can see that it's more concentrated at the ends or the poles. You see these kind of circular lines that are forming in between them, and it kind of looks like this. So we knew about magnets. We also knew about certain properties of magnets like this. So one of the first useful things that magnets would do is if you hung them, let's say on a piece of string. Let me do a different color. If you hung them on a piece of string, they realized that it always oriented itself a certain way. So if we were at Florida and we had a piece of magnet and we hung it, it will always orient itself with one end pointing towards the geographic north, and the other end is going to point to the geographic south. So remember, north and south were just made up names for the top part of the earth, the bottom part of the earth, but since magnets always orient themselves, if you let it hang freely, it's going to orient itself where one side of it is going to point to the north. So we're going to call that the north side of a magnet. And the other side is going to be the south. So that's how we define the two poles of a magnet. One side will always point to the north. The other side will always point to the south. Now, let's summarize kind of the different properties. With the iron filings, we were able to see that it had, it was a field force. And what do I mean by that? It's kind of like gravity. You don't have to physically touch something in order for it to have a force upon you. So it attracts to iron before it physically touches it. Even though on that paper, even though it wasn't physically touching it, go back to that picture. So these are kind of physically touching it because let's just say like the paper is really thin, but these iron filings out here are not, right? But yet they're still affected by the magnet that should be right here, all right? So it's a field force. Next, from the iron filings, we know that we see there's magnetic lines, field lines. They kind of go hand in hand. We see that it's more concentrated at the poles or the ends. And what's neat is that the poles point to either the geographic north or south. That's cool. Now, another thing that we discovered really quickly is that it has certain properties. And this is probably something that you knew as a kid, that north and south attract. Same thing happens with south and north, doesn't really matter. But similar stuff, north and north, south and south, they repel. So very similar to how electrons and protons work. If they have opposite poles, they attract. If you have similar poles, they repel. So that's a cool property that they have. Let me kind of pull up some pictures to kind of explain that. Alright, so like I said, I'm going to show you some pictures that could kind of help explain this part right here. So in these pictures we have two magnets. You could tell this side is the north, this side is south, because that's what's defined. You have iron filings that's shaken on it, and you'll see there's a difference. When it's opposite, these iron filings are kind of attached to each other from the south end to the north end. When they're both similar charges, you'll notice that you get repulsion. Iron filings kind of are cool because it kind of follows the magnetic field lines that are there. So you can see in the first one, the field lines connect to each other, and on the bottom one, they get pushed away. Here is another example of the same thing. On the top, you can see the colors are telling you which ones are north and which ones are south. On the top, they are opposites, and then you can see that the lines connect to each other. And then to the south, they get pushed away. So that's one cool another cool aspect of magnets. Now, if we come back to this picture and we think about that, all right, if magnets are attracted to its opposite charge, then technically, if Earth was a gigantic magnet, even though this was the geographic north, it is technically the south of a magnet, and this is technically the north of a magnet. So it's kind of weird, but that's just how we defined magnets. Remember, the north end of the magnet points to the geographic north. The south pole of a magnet points to the geographic south. Now, we also know that they attract opposite poles. In that case, the Earth has to be south magnetically on top and north magnetically on bottom. Now, this could change. It could flip. So if you Google why we even have a magnetic pole, a quick summary is because most of the core is made of iron, and as it kind of as a liquid form, the Earth is spinning. Remember, it's rotating around in this direction, and that spin is going to cause certain currents within the core itself, and that orientation of the iron molecules inside Earth will create a gigantic magnet. And it'll make more sense as we talk about electron spin. So where do these properties come from? Well, it actually comes from the fact that we have electron spin. You have within your objects electrons that are oriented up or down. I did forget something, so let me go back. One last thing is here is a magnetic bar, a bar magnet, and you see that in the blue we have magnetic field lines. In the black we have arrows. So what are these arrows? Well, they represent mini compasses. So if we go back to the Earth picture, if we put a compass right here, and a compass is just a magnet that's freely rotating in a little device. If I put a magnet, let's say the tip is usually designated as north. If I put it here, eventually its orientation is going to go this way. Now, another useful fact is, as we're doing this, we'll notice that if we put the compass here, it's going to be pointing down. If you put it here, it'll be pointing out. So what it's going to do is going to follow, this compass is going to follow the magnetic field line direction. But it's always, the arrows are always going to point to the North Pole, and the arrows are always going to come out of the south. But remember, this is the south side of a magnet, this is the north side of a magnet. So if we go back to that picture, here's the magnetic fields. And the blue is kind of like, just like if you shook iron filings on it, you'll notice that it circles around the north to the south. It's concentrated on the north and the south. That's where it has the most strength. As it goes around, it loses some strength. So you'll notice in the middle, even though it's magnetic still, it's not as strong because the field lines aren't as concentrated compared to the poles. Now, the arrows are just a convention that we created to help us understand the difference between the north end and the south end. Arrows come out of the north and into the south. And that's a man-made concept. So there is no arrows in real life. It's just how we understand or distinguish between the north end and the south end. Now, back to electron spin. So what we have here is a very interesting fact that iron, nickel, cobalt, these three transition metals right here have very similar properties when it comes to magnets. Now, some of these other transition metals will show some signs of magnetic material, but the main ones are these three. These are called ferromagnetic materials. Kind of to understand why they're significant, let's look at the orbitals. This is the s orbital section. This is the p orbital section, and these are the d, the transitional. So if you remember from chemistry, you have something like 1s, 2s, and then 2p. When you're filling this up with electrons, you always fill with one spin up, one spin down. And when you get to the p's, you fill them all up a certain spin before you fill them up another spin. Imagine these electrons as mini magnets. As it rotates around the atom, it's also rotating around its axis. That spin around the axis gives it a magnetic property. For most elements, they kind of cancel each other out because they get filled up or just because of the structure itself. For some reason, in iron, nickel, cobalt, their spins result into magnetic properties. Okay, like I said, there's no super great answer for that. It's because you would think that this row would be more magnetic than these three because they all have the same outer shell compared to these three, but it is iron, nickel, and cobalt. So all magnetic materials will have one of these or a combination of these three metals in it to be magnetic. Okay, within these three metals, let's say this is iron, and this is cobalt, or sorry, still iron, they have something called domains. And domains are little chunks of the material that have similar magnetic, I guess, orientation. So here is a non-magnet. Oops, non-magnet, just not magnetic. And then this one, this is a magnet. They're both iron, so you could have iron that's non-magnetic, and you could also have iron that is magnetic. And the difference between the two is just the orientation of the domains. Here they're all random, so they kind of cancel each other out. Here they're not random, and they're all kind of facing the same direction. So what will happen is, remember, these little arrows represent mini magnets. This end is eventually going to be the north. This end is going to be the south. And the reason is because as you follow the arrows, remember, arrows point out of the north and point into the south. So that's your north end and your south end. What's cool about iron, nickel, and cobalt is if you do add, let's say, a permanent magnet on this side. So I attach a magnet here that has the north and the south, like so. What's going to happen is it's going to reorient these domains. North end is going to be attracted to south, so it's going to flip this one. It's going to flip this one, and they're going to orient itself kind of similar to this. So you've probably seen this when it comes to paper clips. If you put a piece of magnet on a paper clip, now that paper clip is capable of picking up other paper clips. You magnetized iron, nickel, or cobalt, in this case iron. Once I get rid of this permanent magnet, this paper clip will kind of still keep its magnetic charge for a little bit. But over time, I would say like a few minutes, and it also depends on the paper clip, and it kind of depends on how strong that magnet is. But let's say within a few minutes, it starts losing its magnetic charge. What happens is these domains are going to bounce back to what it originally was. Now, it might not be exactly the same, but remember, this is it takes less energy to maintain this form compared to this form, because these are all in order. Remember, we go from order to disorder. This is disorder, so it takes less energy because they're random, they cancel each other out. Here, they're not random, they're not canceling each other, so that's why this one requires more energy to keep up. Now, how do we even get things like permanent magnets if they kind of do this? Well, most magnets aren't iron, nickel, or cobalt pure. They're a combination of certain metals, certain other alloys. So they might put in aluminum in there. There's a magnet called al-nickel. So that's aluminum, nickel, and cobalt. And you could have ceramic magnets, which have minerals in there. And the goal of having different materials or alloys involved is that it's going to help keep these domains from going back to this. So even if you have a permanent magnet over a long period of time, eventually it's going to lose a lot of its strength. So if you have a really old magnet at home, you'll notice that it just doesn't stick as well once it gets a few years old. It's like really nice magnets will last longer. So neodymium, I believe is how you pronounce it, is the ones that you find in your earphones, and most electronic devices now. If they have a magnet in it, it'll most likely be neodymium, and also the one that I passed out. All right, just as a quick review on terms, ferromagnetic are materials, iron, nickel, cobalt, that not only allow magnetic fields to pass through, but it also has a very strong affinity to them. Paramagnetic will still let magnetic lines pass through, but it's not attracted to them. And diamagnetic are the opposite. They affect magnetic lines and they're not attracted to it. Some actually repel. What's cool is if we watch videos like this, I don't think I could play it on, I could try. I think I can actually. And what I want you to notice on this video is that initially, I think I missed it. Did I miss it? Not yet. The needle's pointing like this, and this person's going to connect it, and you'll notice that it changes direction of the needle. This electricity creates a magnetic field, and this compass is reacting to that. This one's a little bit more obvious. You have a loop, which will explain why it's a little bit more powerful. When they connect it, oh, I think it's reacting from it. Oh, anyway, I missed it, but he'll do it again. Connect it, and it's going to make that needle move. So when you connect or have electrical charge or electrical current going through, that's more appropriate. It creates a magnetic field. And what's neat is that it kind of looks like a certain thing. So here's one video. I'm just going to fast forward it just because we're taking quite a while. And what this person does is he has a wire, iron filing, and he's going to start sending current through it. And when he does, you'll notice that these iron filings will start orienting itself in a certain pattern. So very similar to a magnet. In this video, same person does, oh, I think I did the same video. Here we go. Same concept, but instead of a straight wire, this time it is a loop. And as a loop, it does a certain pattern that's actually quite interesting. So you'll notice that this side is going to act just like a single wire, this side is going to act a single wire, but paired together, they create a pattern that looks like this. And if you do something called the right-hand rule, the arrows are all pointing this way, which then will kind of signify one end as the north and one end as the south. So whenever you see a circular loop of wire, and once you send current through it, you're going to create an electromagnet with one end north and one end south. What's neat is if you kind of compile these loops together, meaning that instead of just having one loop, if you have a bunch of loops like this, it's going to start forming a certain pattern. Now, it will make sense once I kind of describe what the right-hand rule is. So this is kind of a review of those videos. Here, no current, so the compasses or the magnetic, there is no magnetic field. Once there are current, these compasses will orient itself in the presence of a magnetic field, in this case as a circle. Now, we're going to represent this by something called the right-hand rule. So if you have a wire and a current is moving in a certain direction, you're going to grab your wire with your right hand, and it's going to tell you what the magnetic field lines are doing. So right hand rule is you get your right hand, your thumb is going to follow the current, in this case it's up, and I'm going to grab my wire. I can only grab a certain way. I can't grab it, I can grab it this way, but I can't grab it this way. The fact that my fingers only curl around my pipe a certain way or wire, this finger curl, or the way that it grips my pipe, is going to tell me the direction of the magnetic field. In this case, it's going to move counterclockwise. If the current was down, then I have to flip my hand around, do the same thing, but this time my fingers are going to move clockwise. Now, I'm not going to hold you accountable of how to do this because we are online, but I do want you to understand that this pattern forms a certain way. So in a loop, or sorry, in the straight line, it just makes a circular path around the wire itself, which isn't that significant. But once you have in a loop, like I said here, one side becomes north and the other side becomes south. And if we add to it, meaning that if it's not just one loop, but we had a bunch of loops, what's going to happen is these magnetic lines are going to build each other. If it was by itself, we'll just do this. Oops, I got it opposite. If it was by itself, we'll do this. So each one is doing this, and as it's doing that, what happens is they actually build on one another. Whoops, that one's kind of off. So instead of having it go around here, so if they're really dense or close together, you're going to have a magnetic field line that just goes through in the middle, comes out and curls this way. And then all of a sudden you might go, hey, that looks awfully like how a magnetic field line looks in a bar magnet, and it kind of does. So an electromagnet, which is a coiled wire around, creates a magnetic field that looks just like a permanent magnet. What's even better about it is that you're able to turn it on and off, and you're actually able to flip the magnetic field by just changing the direction of the current. All right, with this concept, we're going to explain how motors and generators work next. Hopefully this makes sense, and take care.